Hello, ladies and gentlemen. I'm Associate Professor Xin-Yu, coming from Department of Electrical Engineering, National Sun Yat-sen University, Taiwan, ROC. Here is my pleasure to make the presentation regarding our latest research work. The presentation title is Unified Chip Architecture of Decision Tree DT Online Trainer and Classifier Hardware for various applications. We know that the machine learning ML is very popular now and widely used for many applications, such as channel noise prediction, image recognition, spike detection, treasures detection, and so on. Especially, it needs the property of lightweight and low area cost for the edge computing and portable IoT device. The suitable MLO model is decision tree DT. DT is one kind of supervised machine learning method, popularly used for training, classification, and regression in the current research field. The objective is to build up a tree structure model that predicts the labels of the target data by learning several simple decision rules according to the instance attributes. In the current literature, the DT hardware are implemented in FPGA and ASIC domains. Unfortunately, there is no ASIC chip work with both online training and classification. Therefore, we propose a first DT-based hardware chip simultaneous handling online training and classification machine learning tasks. It's also a unified DT-based ASIC chip for various applications, not supporting only one specific and limited application only. It mainly aims to overcome the situations or environment with rapid changes and elusive conditions. The requirement of online feature is significantly important, especially for the military and aerospace applications. The design goals include 3 points. First, a user-friendly and low-latency training system, which owns the adjustable training parameters and the fast approximate computation. Second, an immediate classification system with high-speed property. Third, an integrated design of online trainer and classifier for general-purpose application used in the advanced scenarios. Here shows our proposed DT system chip design architecture. The hardware architecture consists of 3 subsystems, including Decision Tree Training System, DTTS, Adaptive Means Training System, AMTS, and the Train-Based Classification System, TCS. DTTS is roughly constructed based on conventional DT algorithm, whereas AMTS is built according to the proposed adaptive means algorithm. AMTS is a faster check mechanism to corroborate or with DTTS, providing another splitting choice in the training phase. TCS is only responsible for the classification. The first design technique is the divider-free system in parallel Gini impurity calculation, DRGIC. Instead of the division calculation, it is used to compute the fitting polynomials and the delta function of 3D Gini impurity surveys. The benefit is to dramatically reduce the high latency of the divider in online training. The second design technique is adaptive means with updated learning function, AMUCULM. We don't use the constant converge function due to the instability. The learning function enables the approximates calculation close to the theoretical value, leading to the lower error rate. The third design technique is speeding up classification with double root tree (SCDRT). It is to utilize the feature of the binary tree to unfold it into double roots for further improving the classification throughput. Here shows the finite state machine (FSM) of our proposed hardware architecture. There are three design phases, such as the setup, online training, and the classification. Blue color denotes AMTS. Brown color denotes DTTS. Green color denotes the hardware sharing for the two training systems. Purple color denotes the TCS. With the TSMC 40nm multi-threshold voltage CMOS technology, our proposed system is first designed with Verilog and then synthesis with design compiler tool DC. After synthesis, the ratio of the circuit area using low and high threshold voltages occupies 89% and 11% respectively. The hardware area is only 0.643 millimeter square. It reached a maximum operating frequency of 488 MHz. The critical path time after circuit optimization is roughly dominated by one-stage multiplication. The right figure shows the area distribution of each module in each subsystem. Here shows the ASIC chip layout after the automatic placement layout API with the IC compiler tool. The maximum operating frequency is up to 429 MHz. The total core area of the ASIC chip layout is only 0.896 millimeter multiplied 0.896 millimeters, equaling to the 0.803 millimeter square, while the core utilization ratio is 80.04%. The ratio of the combination logic, sequential circuits, and the SRAM markers is 49.5%, 19.2%, and 31.3% respectively. The coding average power dissipation is only 73.7 milliwatt. Online training latency under the worst-case design emulation is only 9.98 milliseconds for 1K data. For the classification performance, the decision throughput ranging from 4.29 to 8.58 gigabytes per second. In the system verification, we use 7 representative datasets for various applications. The worst-case training latency is only 9.98 milliseconds for 1K data. The classification latency is only 0.877 microseconds for 439 data. The recording accuracy performance is very close to the result of pure DT algorithm in software. As compared to other design works in the current literature, our work is the only one to simultaneously perform online training and classification tasks. Most importantly, only our proposed work can provide online training mission. The training latency is only 9.98 milliseconds in the worst case for handling 1K training data. In addition, our work also possesses a better classification performance than other works, such as 429 mega to 858 mega design per second. Let's take a look at the conclusion. What have we proposed in this presentation? It's a total ASIC solution of DT-based online training and classification in chip implementation. We also propose three useful design techniques: DRGIC, AMULF, and SCDRC. The features include low latency and high-speed properties by diminishing the division and the architecture optimization. Here are the reference. It's the end of our presentation. Many thanks for your listening.